So last week I used our quiz to introduce this concept of angular momentum and did it in such a way where you were looking at two things that were colliding and how did the angular speed change after that collision. So there's a few things that I want to go in a little bit more depth on to help you really solidify this concept. So we remember our linear momentum in terms of just mass and velocity. And so the one thing I was walking everybody through is that here is this conversion between the two. So my mass is my inertia now, and my velocity is my omega. And as you can see, what I have down here is that a change in momentum, or an impulse, remember that's how we defined it in the first quarter, it requires force. So if there is an external force, then momentum isn't conserved. And we can figure out with the change of momentum what kind of force, or how much force rather, was applied. We can also figure out what the acceleration would be. So the same thing with angular momentum. If angular momentum isn't conserved, then I have to have a torque applied. And so we can relate our I alpha right to our torque, and we can do that with just looking at a change in momentum. And here's the fun part about that is we've talked about inertia, and we've used that quite a bit now in several examples. And we have things like we say, okay, so for a point mass, the inertia is what, mr squared, right? And the thing I keep repeating to everybody is to remember the r for, like, when we're rolling the discs and whatnot down the hill, tends to be the radius. But what it actually is defining is the distance away that the center of mass is concentrated from the axis of rotation. So one of the real life things, if you've ever watched the Winter Olympics or you're a fan of figure skating, is when the skaters are out on the ice and they have their arms wide out, spread out, and then they pull them in, and then they spin so fast that I don't know how they don't get dizzy and fall down, but they speed up. Well, what's happening is they're changing their inertia. So out here I have a larger inertia because I have a wider radius. I pull my hands in, I have a smaller radius, a smaller inertia. So by conservation laws, then what has to change? I'm going to have something that looks like this, right? Where we could say, well, I omega naught, or initial, equals I omega final. Well, we look at this, and in last quarter, or first quarter, I was mass, and yeah, we'd change that when we'd have like a collision. But if I don't have a collision, you would look at this and say, well, my omega final must be the same as my omega initial. But if I throw this in there, that here's my mr squared omega naught equals mr squared omega final, and then I remind myself that this is changing. So this one would be smaller, so we'll call this R2, than that one. So if I know how much my radius has changed, the distribution of mass from my axis of rotation, then I can figure out how much faster I'm going to be going. And so that's some of what we're going to do today to get you finished ready for our first exam. Okay, so here's our first example. I have two disks that are rotating, and I know the velocity that they're rotating. I'm sorry, the rotational speed. So I have the 50 radians per second for R1, which is going to be this bigger one. So this big one is like going like that away at 50 radians per second. And we're told that they're going in, we're told that they're rotating in the same direction. So it doesn't much matter. If you decide that they were rotating in the other way, it's not going to change a thing. See, so this one here, the smaller one, is doing what? It's rotating at 200 radians per second. So we have two disks. What are we going to have? I'm going to have, let's call this mass 1 and this mass 2. And let's think, they're going to collide, and we want to figure out how fast they're going in the end. So in linear momentum, what would we do? We'd be like mass 1, velocity 1, plus mass 2, velocity 2, and reminding ourselves that these things are vector quantities. So if they're going in the same direction, you might as well define that direction as being positive. And then what's that going to equal in the end? It's going to equal mass 1 plus mass 2, because they've combined, and some final V final. So do we know here? We know the masses of each thing. We know the radii. So remember, mass goes to inertia. So inertia 1, omega 1, plus inertia 2, omega 2, equals the sum of my inertias, because now they're combined, times my omega final, omega prime, if you will. So I look at what information I've been given. What do I need? I need to know what the inertia of a disk is. So take a second and look that up, and then come on back. Okay. So if you looked it up, you know that the disk inertia, so I of, oops, that's not a pen anymore. I of the disk is 1/2 mr squared. And so what do we have? I'm going to go ahead and write it over here, so it's going to have a little bit more space. So I have 1/2 mass 1 r1 squared omega 1 plus 1/2 m2 r2 squared omega 2 equals 1/2 mass 1 r1 squared plus 1/2 mass 2 r2 squared times omega final. And the reason why I go ahead and write all that out instead of just putting it into my calculator, if I want to like minimize the amount of button pushing I'm going to do, I look at this and I've got a 1/2. Whoops, nope, I can't. That's going to become 1. Nope, I can. I can factor that out. Yeah, so I'll have a 1/2 and everything, so I can cancel it out. Magic. All right. So my mass 1, we can kind of look at this. Mass 2 is a bit bigger and a larger rotational rate and a smaller radius. So what do you think is going to happen when we put these things together? Do you think that, I'm going to try to talk and write, that my final angular speed is going to be much larger, just a little bit larger, or smaller? Omega 1. See, I can't write and talk at the same time. We just have proof of that. So plus mass 2, 4 times 0.1 squared times 200. Oops, we want omega final. So let's just go ahead and divide this now by my sum of my inertias. So mass 1, 2 times 0.2 squared plus 4 times 0.1 squared will give us our omega final. And so what do we get in the end? I get in the end that I'm going 100 radians per second. What? Why do you think that is? Why do you think I slowed down? They're both spinning in the same direction, and they're combining. So your instinct might be that they're going to speed up a bunch or speed up just a little bit, but they've slowed down. So what do you think is happening in terms of inertia? I put these two masses together, right? So I've combined these two disks. I no longer have like this nice, pretty, evenly distributed mass. Now I have like almost like this awkward stack of masses spinning. So when I put those two things together, if I look at this center one, this one is more massive with this smaller radius. And here's the axes, right? So I'm going to have a greater amount concentrated, like once they're combined, around here, but I still have a fair amount of mass on the outside. So by both combining the masses and having now this kind of odd distribution for my inertias, I'm actually slowing down. Pretty cool. So the last little thing that I ask on here is, how do you think this is going to change if they're initially rotating in the opposite directions? So play around with that. I mean, obviously we've seen that the speed's going to decrease, and so if they're going in opposite directions to begin with, it's a good indication that they're definitely going to slow down. But play with the math and see by how much do they slow down. And you can change it, make this one, it's not going to matter. So just have one of them rotating one direction, so you just throw in a negative sign in there somewhere. And see what happens to change the direction. A, do I change direction? And B, by how much do I slow down? So that'll be a good one. So play with that.